In mathematics, an iterated function is a function xx which is obtained by composing another function f xx with itself a certain number of times. The process of repeatedly applying the same function is called iteration. In this process, starting from some initial number, the result of applying a given function is fed again in the function as input, and this process is repeated. Iterated functions are objects of study in computer science, fractals, dynamical systems, mathematics and renormalization group physics. Definition. The formal definition of an iterated function on a set X follows. Let X be a set and f xx be a function. Define Fn as the nth iterative f, where n is a non-negative integer, by, and where idx is the identity function on X and fg denotes function composition, that is, equals f, always associative, because the notation Fn may refer to both iteration of the function f or exponentiation of the function f. Some mathematicians choose to write f degree n for the nth iterate of the function f. Abelian property in iteration sequences. In general, the following identity holds for all non-negative integers m and n. This is structurally identical to the property of exponentiation that m equals m plus n, i.e., the special case f equals ax. In general, for arbitrary general indices m and n, this relation is called the translation functional equation, cf. Schrodinger's equation and Abel equation. On a logarithmic scale, this reduces to the nesting property of Chebyshev polynomials, trademark equals trademark n, since Tn equals cos. The relation n equals m equals f. Minnesota also holds, analogous to the property of exponentiation, that n equals m equals amn. The sequence of functions Fn is called a Picard sequence, named after Charles-Émile Picard. For a given x in X, the sequence of values Fn is called the orbit of X. If Fn equals Fn plus m for some integer m, the orbit is called a periodic orbit. The smallest such value of m for a given x is called the period of the orbit. The point x itself is called a periodic point. The cycle detection problem in computer science is the algorithmic problem of finding the first periodic point in an orbit, and the period of the orbit. Fixed points. If f equals x for some x in X, then x is called the fixed point of the iterated sequence. The set of fixed points is often denoted as fix. There exist a number of fixed-point theorems that guarantee the existence of fixed points in various situations, including the Banach fixed-point theorem and the Brouwer fixed-point theorem. There are several techniques for convergence acceleration of the sequences produced by fixed-point iteration. For example, the Aitken method applied to an iterated fixed point is known as Stephenson's method, and produces quadratic convergence, limiting behavior. Upon iteration, one may find that there are sets that shrink and converge towards a single point. In such a case, the point that is converged to is known as an attractive fixed point. Conversely, iteration may give the appearance of points diverging away from a single point. This would be the case for an unstable fixed point, when the points of the orbit converge to one or more limits. The set of accumulation points of the orbit is known as the limit set or the omega limit set. The ideas of attraction and repulsion generalize similarly. One may categorize iterates into stable sets and unstable sets, according to the behavior of small neighborhoods under iteration. Other limiting behaviors are possible. For example, wandering points are points that move away, and never come back even close to where they started. Fractional iterates and flows, and negative iterates. In some instances, fractional iteration of a function can be defined. For instance, a half iterate of a function f is a function g such that g equals f. This function g can be written using the index notation as f1/2. Similarly, f1/3 is the function defined such that f1/3 equals f, while f2/3 may be defined equal to f1/3, and so forth, all based on the principle mentioned earlier, that fm/fn equals fm plus n. This idea can be generalized so that the iteration count n becomes a continuous parameter, a sort of continuous time of a continuous orbit. In such cases, one refers to the system as a flow, specified by Schrodinger's equation. Negative iterates correspond to function inverses and their compositions. For example, f-1 is the normal inverse of f, while f-2 is the inverse composed with itself, i.e., f-2 equals f-1. Fractional negative iterates are defined analogously to fractional positive ones. For example, f-1/2 is defined such that f-1/2 equals f-1, or, equivalently, such that f-1/2 equals f0 equals x. Some formulas for fractional iteration. One of several methods of finding a series formula for fractional iteration, making use of a fixed point, is as follows. First, determine a fixed point for the function such that f equals a. Define fn equals a for all n belonging to the rails. This, in some ways, is the most natural extra condition to place upon the fractional iterates. Expand fn around the fixed point or as a Taylor series. Expand out, substitute in for fk equals a for any k. Make use of the geometric progression to simplify terms. There is a special case when f equals 1, when n is not an integer. Make use of the power formula yn equals exp. This can be carried on indefinitely, although inefficiently, as the latter terms become increasingly complicated. A more systematic procedure is outlined in the following section on conjugacy. Example 1. For example, setting f equals cx plus d gives the fixed pointer equals d, so the above formula terminates to just, which is trivial to check. Example 2. Find the value of where this is done n times. We have f equals square root 2x. A fixed point is a equals f equals 2. So set x equals 1 and fn expanded around the fixed point value of 2 is then an infinite series, which, taking just the first three terms, is correct to the first decimal place when n is positive. Cf. Tetration. Fn equals n square root 2 equals 4 causes the series to diverge. For n equals -1, the series computes the inverse function 2ln x, lane 2. Example 3. With the function f equals xb, expand around the fixed point 1 to get the series, which is simply the Taylor series of x expanded around 1. Conjugacy. If f and g are two iterated functions, and there exists a homeomorphism H such that g equals h-1 fh, then f and g are said to be topologically conjugate. Clearly, topological conjugacy is preserved under iteration, as gn equals h-1 fnh. Thus, if one can solve for one iterated function system, one also has solutions for all topologically conjugate systems. For example, the tent map is topologically conjugate to the logistic map. As a special case, taking f equals x plus 1, one has the iteration of g equals h-1 plus 1, as gn equals h-1 plus n, for any function h. Making the substitution x equals h-1 equals yields g equals, a form known as the Abel equation. Even in the absence of a strict homeomorphism, near a fixed point, here taken to be at x equals 0, f equals 0, one may often solve Schrodinger's equation for a function psi, which makes f locally conjugate to a mere dilation, g equals f, x, that is f equals psi-1 psi. Thus, its iteration orbit, or flow, under suitable provisions 1, amounts to the conjugate of the orbit of the monomial, psi-1 n psi, where n in this expression serves as a plane exponent. Functional iteration has been reduced to multiplication. Here, however, the exponent n no longer needs be integer or positive, and is a continuous time of evolution for the full orbit. The monoid of the Picard sequence has generalized to a full continuous group. This method is equivalent to the algorithm of the preceding section, albeit, in practice, more powerful and systematic. Markov chains. if the function is linear and can be described by a stochastic matrix, that is, a matrix whose rows or columns sum to 1, then the iterated system is known as a Markov chain. Examples: there are many chaotic maps. Well-known iterated functions include the Mandelbrot set and iterated function systems. Ernst Schroeder, in 1870, worked out special cases of the logistic map, such as the chaotic case f equals 4x, so that psi equals arcsine 2, hence fn equals sin 2. A non-chaotic case Schroeder also illustrated with his method, f equals 2x, yielded psi equals -1/2 lane, and hence fn equals -1/2 2n minus 1. If f is the action of a group element on a set, then the iterated function corresponds to a free group. Most functions do not have explicit general closed-form expressions for the nth iterate. The table below lists some that do. Note that all these expressions are valid even for non-integer and negative n, as well as positive integer n. Note: these two special cases of x2 plus bx plus c are the only cases that have a closed-form solution. Choosing b equals 2 equals a and b equals 4 equals a, respectively, further reduces them to the non-chaotic and chaotic logistic cases discussed prior to the table. Some of these examples are related among themselves by simple conjugacies. A few further examples, essentially amounting to simple conjugacies of Schroeder's examples, can be found in Ref. Means of study. Iterated functions can be studied with the Artin Mazur zeta function and with transfer operators. In computer science, iterated functions occur as a special case of recursive functions, which in turn anchor the study of such broad topics as lambda calculus, or narrower ones, such as the denotational semantics of computer programs. Definitions in terms of iterated functions. Two important functionals can be defined in terms of iterated functions. These are summation and the equivalent product. Lee's data transport equation. Iterated functions crop up in the series expansion of the combined functions, such as g, given the iteration velocity, or beta function. For the nth iterate of the function f, we have, for example, for rigid advection, if f equals x plus a, then v equals a. Consequently g equals expg, a plane shift operator.